All right, about 40 seconds until day 15 starts. Let's check the leaderboard. Looks like Sergey pulled up into second place, putting Top Climb in first and Anonymous User in third. And we're at almost 60 people now that have completed every day, which is absolutely dope. Love to see that. So for day 15, we've got the Beacon Exclusion Zone. Deployable sensors, determine the position of a beacon precisely. Sensors can only lock on to one closest to the sensor as measured by the Manhattan distance. There's never a tie where two beacons are the same distance. It doesn't take long for the sensors to report back. Here we go. I feel like we have one of these problems every year with the Manhattan distance and like these locations. So this is the puzzle input. We'll grab it and throw it in over here because we're going to have to parse it. So consider the sensor at 2.8. The closest beacon is negative 215, 218, negative 215. For 916, which is this one, closest is at 1016. 1016 doesn't show up on the left-hand side. So drawing sensors as S and beacons as B, the above arrangement of sensors and beacons looks like this. Sensor, beacon, sensor, beacon. This isn't necessarily a comprehensive map, yada, yada. So the sensor's closest beacon is at 210, so you know where there are no beacons that are closer. You'll need to work out where the distressed beacon is by working out where it isn't. For now, keep things simple by counting the positions where a beacon cannot possibly be along just a single row. The coverage from all sensors near that row looks like this. In this example, in the row where y equals 10, there are 26 positions where a beacon cannot be present. Consult the report from the sensors you just deployed in the row where y is 2 million. How many positions cannot contain a beacon? So the answer is 26 for the test input. I wonder, yeah, these are completely wherever they happen to be, so we can't rely on it like starting at 0 or anything like that. This is only within like, I don't know, 20 or whatever. So algorithmically, I don't know any shortcut here. I don't know any I don't know what algorithm this is describing, if there is one. So naively, I think the only thing I can do is determine the distance between a sensor and a beacon and try to fill in the spots that it could be. So if S to B is what? If we get the Manhattan distance from S to B, then we have the ability to test whether a given point is close enough to a sensor to be filled in. We could potentially bound that somehow. What is a row is a question in my head. Like, is a row from the leftmost beacon to the rightmost beacon? Right? Like they show from left 0, 1, 2. They show beyond that. 0, 1, 2, there's that beacon. But in row 10 in the answer, they show negative 4. How are we defining the grid? Because if we go too far, we can have an infinite number of like unlit beacons or whatever. How do we know what the grid is? Because this answer shows grid starting from negative 2 here, but it shows the answer is starting from negative 4. Yeah, negative 4 here. So is it the sensor distance that defines our answer? Well, I guess we could pull this into a map at least, and then we could always turn it into whatever we need it to be. So let's start with that. It feels a little weird to have a different type for both of these. They're going to be the same, right? We have an X that's an I-32 and a Y that's an I-32. But I think for our purposes, they are going to be at least processed differently. So having the keys be the sensors and the values be the beacons is probably going to serve us. I'm going to make a reusable position parser that returns the X and the Y. So it's going to be like separated pair, preceded, if I can remember how to spell it, tag X equals nom character. I brought in complete, didn't I? So complete I-32, and then preceded tag Y equals complete I-32. And in the middle here, we have to have a tag for comma space. Got to make sure we import anything that we don't have not imported. This, of course, is not the right return type, so that's why we're seeing red. So this is a single position, which means that our map is going to be a separated list 1, line ending, and then we get a preceded tag sensor at separated pair, position tag closest beacon is at position. And we'll map this XY to sensor, and this will be dot mapped to beacon. And I wrote my map function wrong, so I just need to make sure that this is a tuple because that's what position returns in its success case. I don't have a B tree map in scope, so we'll bring that in. And then this is a separated list, and the list is sensors and beacons as tuples. So it should be able to do list.iter.collect, and we'll specify that we want to collect it into this, and we end up with expected result string slice B tree map sensor beacon found struct nom map impl fn mute, because we aren't passing in the input. Oh, separated list doesn't have a map. That's the problem. So let's do something a little bit simpler here. Separated list doesn't have a map because it's not a parser. It's a combinator that applies parsers. So it doesn't implement the parser trait. So input, what do we call this? List equals this. We get the return value out of it. We no longer need map, but we do need to do okay input like this. And we've got a type error. So what do we have? A value of type B-tree map sensor beacon cannot be built from an iterator over elements of type. So we probably just want to own this stuff anyway, because we're returning it all. So we'll into iter. We don't have derive ord. Of course we don't. We don't have ord derived for sensor. Okay, so we can do derive ord, partial ord, eq, and partial eq, and we don't need to bring anything into scope to do that. We are ignoring test 2. So this should give us the map that we want. I didn't implement debug for it, so let's do let underscore map equals, did I call this map? Yuck. Oh well, that's what I did. Unwrap, this is a to-do, debug map. It's going to require us to implement debug for the types. I'm just going to copy and paste it out of the Rust compiler error message here. If you're unfamiliar with the error message, it says beacon doesn't implement debug because we're using the debug macro to format it using the debug formatter. So we need that. Oh, I copied that. Dang. So we get debug here, and we can add debug here. That should solve our problems. We'll get rid of the B-tree set from yesterday. So we have a bunch of sensors and a bunch of beacons. Looks like sensor at 218, beacon at negative 215. So yeah, I mean, that seems fine. And we have them like in order or whatever. The order here doesn't super matter. So what do we do with this information? I think Manhattan distance is just like x minus x kind of thing. And we probably need to calculate that for everything. So I'm going to iter.map with sensor and beacon. I forget if those come in as tuples off a iter. We're going to have to collect here. And we're going to make this a B-tree map from sensor to, we'll make this an I32. I'm making it an I32 so that it matches with the other numbers, basically. There's no strong reason to choose an I32 because I'll be doing an absolute value on these anyway. So map sensor beacon gives us sensor, and then let's check to see to make sure that this is valid first. I think that it goes the same number in each direction, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think that once we have a distance of 9, then we're good. So we go 9 in each direction. So the beacon here is 1, 2, 3, 4, 5, 6, 7, 8, 9 away. So that should work. So we have 2 choices here. I'm going to take the absolute value approach. Beacon.x minus sensor.x.abs. Beacon.y minus sensor.y.abs. And then I believe that these are actually a tuple. And now we read the compiler information. Value of sensor I32 cannot be built from this tuple. That's correct. So I think we just add these together, right? The distance for X and the distance for Y, absolute valued. And then we will clone these. I mean, these can be references. It doesn't really matter to us. So I'll make them references and not do any cloning or whatever. So now we have the distances for every sensor, and we need to filter for any sensor that can reach line 10. I'm just going to keep collecting these in case I have to debug them out for debugging purposes. So if we have the distances, then we can filter for sensor distance, and we have some number here. So it's like let line number equals 10 in this case. Then we've got sensor, what? Sensor X and Y, or sensor positive and negative Y, or rather, I misphrased that. Sensor plus distance, sensor minus distance, and we'll call this sensor range. It's literally a range for the sensor. Sensor range dot contains line number, right? Because it has to be able to reach that. This doesn't run because we're not doing anything with it. If we have, let's map over sensor range here, and let's change this into a filter map. And then if this contains that, then we return some sensor range, right? Else none. Line number probably needs to be a reference. Sensor.y up here. This huge yellow warning here is because we aren't using the iterator. So if you don't have .collect on the end and you're running like Rust Analyzer or something, it will warn you. See if I can find the warning. Here we go, right here. Iterators are lazy and do nothing unless consumed. All iterators in Rust are lazy. There is a macro called must use that you can put on stuff. So like I could do this kind of thing, must use. And what that means is that the value must be used, basically. The Rust compiler must check that this thing has to be used or accessed kind of thing. So in this case, what we're doing is we're doing distances.iter.filtermap.map, but we don't have any finishing function on the end. So we're not actually calling the iterator. We're just setting the iterator up. So that's why it's yellow. We've got sensor and range, and then we need what? We need the lowest position in 10. Is it the lowest position in 10? I still am confused as to how wide this row is. Oh, good. We only have to detect the sensor positions. Okay, so we don't need to care about how big the row is. So we probably don't want sensor range here. Or rather, we know at this point that the sensor covers that line in some respect. So we could do, I think we could do something super naive, like generate all of the XY positions that a sensor could be in. I don't think we need to do all of that though. So I'm trying to think about how to cut that down. So maybe we don't need range. We can always reconstruct range. So I'm going to remove the map here for a second and just do contains. And then why did that change my math? So I wasn't quite paying attention and I'm not sure why these needed to be dereferenced now, but they do. So sensor range contains line number. We map. This is the distance still. So we've got, in this case, we've got S that is 1, 2, 3, 4, 5, 6, 7, 8, 9 away from B. It is at 7, 8, 8, 7. So that means that horizontally at our 0 point, we are 9 on the left and 9 on the right. So we are a width of 19. So it'll always be odd and end in 1. So we can remove 2 from each. So we can, distance times 2 plus 1 is the width at the center point of the sensor. And then we need sensor.y minus line number, right? So I think I want the actual cell positions. So if we have the sensor XY and we have the line number that we need to target, if the sensor is below, so Y is greater, then it'll be like 15 minus 10, which will give us 5. It's a distance of 5 away, but that distance is in the negative direction. If it's lower and sensor.y is 5, then it's 5 minus 10, and it's negative 5. So we can like 0 dot dot this number, signum. So this is the distance to the line. Signum will either be negative 1 or 1, if I remember correctly. So returns the sign of a number. For F32 and F64, it's 1.0, negative 1.0, or one of these others. If it's for a signed integer, like an I32, we get 0, 1, and negative 1. So that's signum here. So we've got the distance to the line. So either 15 minus 10 or 5 minus 10, which will give us either 5 or negative 5. We get the signum out of it. And I guess we can just directly calculate the width, right? Width equals distance minus distance to line, absolute value, times 2 plus 1. So we don't need this original distance calculation. We can just do it down here. Let's call this max distance, just to differentiate it from other stuff. So we've got the width, and we need to center that on the sensor at 10. So I don't think it matters which direction we go in, because we already know what we'll cover. So we can do, so actually we can do, get rid of this times 2 and the plus 1. And this isn't width necessarily. This is max distance on line. And then this is sensor.x minus max distance on line dot sensor.x plus max distance on line. If my math is correct, I think this gives us a range of all of the points that are on the line for the x's anyway, which is all that matters because we know which y we're on. So can we just collect this? If we flatten this and then we turn this into a vec of I32s, do we even need the flatten? Yeah, we're gonna use the flatten. Let x positions equals this. And then I guess it's like x positions.length.toString, right? If we did all the math correctly, which is highly suspect. Okay, so we've got 28 and 26. So we're above by 2. You can see Rust warning us that we didn't use direction to line. We don't actually need the signum for any reason, it doesn't look like. And because we got rid of this other math, these extra parentheses are extra. The problem here is that I didn't do an inclusive range, which sticks us way higher as well. So let's not inspect here, and we'll do debug range. So I've got -2 to 2, 2 to 14, 12 to 12, which is just one spot, 14 to 18, and 16 to 24. So if we look at line 10, we got -2 to 2, right? -2, 1, 2. Got 2 to 14, which is here. 12 doesn't matter, 14 to 18, and then 16 to 24. 16 to 24. That looks correct. There are 26 positions where a beacon cannot be present. We've calculated all of these spots, but the count is wrong because we're not uniquing them. That's the problem. And unique here that I'm using is from itertools. So I've got 27 and 26, which is what we've got -2 there. Oh, yeah. So we need to remove the potential positions that a beacon could be in. So let's take this and we will drop it down a couple. So we've flattened already, and then we've uniqued, which gives us all of the integers here. So flatten is evaluating these ranges for us. This could actually just be flat map. So let's make that flat map. And then we unique them, we inspect them, we end up with the full list of X positions that we need, and we need to do a beacon iteration. So it's going to be map.values that contains X10, X line number. This is going to have to be beacon X, Y, and then this has to be a reference because it's contains. So we're constructing a beacon every time, which is whatever. We don't derive partial equality for the values. So we don't have a beacon equals beacon right now, which we can solve by doing partial equality. And then X will be X, the reference to the value. And we need to flip this. So not contains. So we're checking for the beacons, or we have all of our X positions, right? And we filter over those. And we're checking the beacons values, which is map.values. And we're seeing if any beacon matches this X position with the line number position. And we want to filter out any of them that do. So we do not. That seems to work. So let's try it on the full input. I feel like I'm doing a lot of work here that I probably don't need to be doing in the solution. Oh, we don't want to do, we don't want to have to print out to the console for every number. That would be slower than actually running the program itself. So I'm going to run this in release mode to start off, and we get this number, 5,289,444. It's not the right answer. That's not great. Oh, you know what the problem is? Oh, what a silly mistake. Okay, so we need this function that we have for process part 1 to accept this extra number. So let's add line number as an argument there. Let's do 10 for the test, which should still pass. And part 1 here is going to accept this number, which I'm going to add our underscores to make it more readable. So that, remember, this is our binary. So it's the thing that's calling process part 1 for our file out here. And then this is the test for process part 1. So if I run cargo test now, everything compiles, our test passes, and then we run part 1. That is the same answer though, isn't it? Oh, right, because you know what I did? I left it in. I redefined it in the middle of the function. I used the same variable name here as I did on line 66, and we're just going to remove line 66, and this should give us a new answer, 5,299,855. Just make sure cargo test still works. Yep, and we'll pass this in. Gold star. Okay, so let's cover what we did. It's a little bit messy. So we've got this line that is like sensor at x equals 2, y equals 18. We wrote a parser for just this segment, and then we did a split pair parser with the middle being closest beacon is at. So we got position, split, position, and then we preceded that parser with sensor at for every line. So the way that looks is this map parser gives us a separated list 1, which is a line ending, which is either new line or /r /n, preceded with sensor at, separated pair. So inside of here, we're into each line. Every line is preceded with sensor at, and then has a separated pair that's separated by the tag closest beacon is at. Each of those is a position. One of them is a sensor. One of them is a beacon. The position parser is a separated pair itself with x equals some number, a comma, and then y equals some number. And then to return this value, we want to collect it into a B-tree map. Why a B-tree map? Because I felt like it. I don't really have a reason for that. It could easily just have been like a tuple or something like that. But we do need to, when we do our processing, we need to iterate over sensors and beacons, as well as iterating over just beacons later. So mildly useful, but we could have done it other ways. So we get this map. This is this B-tree map of sensors and beacons. Remember, you can put complex values in for the keys in Rust for B-tree map. So we iterate over that whole B-tree map, and we map the sensor and beacon to the sensor and the distance from the sensor to the beacon, collect that into a B-tree map of sensors and their distances, which we then immediately use. So we probably don't need to collect here because we're just going to iterate over it again. So if I did this and just removed all of that, then we have distances up there, which is actually X positions. No, there's something else wrong there. Oh, because we specify the type, I think, and the return type there is no longer that. And then the values here change, and I think that that would be fine. So we could do this as one long chain if we wanted to. But for clarity, because I just wrote it like this, I'm going to leave it like that. So we get the distances. We get a B-tree map of the sensors and all the distances to their beacon using what's called Manhattan distance, which is just x minus x absolute, y minus y absolute. The thing that we try to get to is having all of the x positions on whatever line we're looking for. So we take all of those distances, we filter out for any sensor range that contains the line number that we're looking for. So we calculate the sensor range by taking the y value of the sensor, subtracting distance and adding distance, and that gives us the lower bound and upper bound for y indexes that the sensor range can reach. If that sensor range contains the line number we're looking for, we know that that sensor can reach that line. So we flat map here because we're returning a range at the end and we want that to be evaluated into individual integers. And we get the sensor and what I'm calling the max distance, which is the same as distance in this case. So the distance to the line that we're looking for is the y index of the sensor minus the line number. So this gives us how far we are away from sensor to the line that we're looking for. So the max distance on line is something that we need to calculate for the x direction. So we take the maximum distance that it could possibly be, so 9, let's say, and we subtract how far we are away from that line. So if we are at, say, 19, right? If our max distance from sensor to beacon is 19 and our distance to line is 9, we end up with a max distance on line of 10. And the max distance on line is how far we go out in the x direction on one axis on that line. So we take the sensor x and we remove that segment on the left-hand side, and then we include that segment on the right-hand side, and we create a range from that. So we've got every x value that our sensor range has sort of gone down into. And you can kind of see more obviously what I mean here. So we're going from the sensor up to say, let's say, for example, line 3. If we go from S to line 3 here, the max distance is this number here. So this is 9, right? And then it is 8, and then it's 7, and then it's 6, and then it's 5. So 9 full distance minus 4 to line 3 is 5. So it gives us this left-hand side here. We then need to do this x all the way up to this x, and that gives us the range of all the x values. We do a unique because this is going to end up being multiple different ranges, and they're going to be overlapping. So we only want to get the unique x values, and then we filter that out by checking to see if any of those x values match a potential beacon, because we want to filter out any beacons that are actively being sensed from the result set for the purposes of what the question wants us to do. We collect that into a vec of i32s. We could just count here, though. Like this could be count toString, and then we could get rid of x positions. And if we cargo test, this also works. So we get the number of x positions that are on that line that are unique, that don't include a beacon, and we return it. It's notable to say that unique is from the itertools trait, which I'm bringing in above. So just be aware of that if you're trying to use that and only using the Rust standard library or something. So that brings us to part 2. So our handheld device indicates that the distress signal is coming from a beacon nearby. The distress beacon is not detected by any sensor, but the distress beacon must have an X and Y coordinates no lower than 0 and no larger than 4 million. To isolate the beacon signal, you need to determine its tuning frequency, which can be found by multiplying its X coordinate by 4 million and then adding its Y coordinate. Okay. In the example above, the search space is smaller. Instead, the X and Y coordinates can each be found at most 20. Oh, from 0 to 20 instead of 0 to 4 million. Is that what it's saying? With this reduced search area, there's only a single position that could have a beacon, 1411. The tuning frequency is this. So let's say that our answer is going to be some beacon.x times 4 million plus beacon.y. So whatever happens, this is our answer. It's beacon.x times 4 million plus beacon.y. Let's say lower bound and upper bound could be here. So we need to search the entire space. So if we, I'm doing some simple math here. If we try to generate all of the space, then we end up with whatever that number is, 16 trillion. Yeah, so 16 trillion. That does seem like a lot. We could generate all of the ranges, which would probably be less. We would still need, at least 4 million times however many are in each line. There's got to be a better way to find this position. I do think this will actually be an interesting case to use maybe DAT and criterion on. So let's at least write the simple one, and then we'll worry about doing it for the larger input. So process part 2 has to take a limit, and we are looking for this number. The limit for the test is 20. The limit for part 2 is 4 million. So if we're going to do this, I think we have to calculate the distance for all the sensors at least, and then we can do a distance calculation to every point. So I think we have to start off with this distances. So we get a distance from the B-tree map to every beacon, let's say, or to the closest beacon anyway. And then we do something super naive like 0 dot dot equals limit, Cartesian product, 0 dot dot equals limit, find x, y. I think realistically, if we want this to go down like a y and then go down and then go down and go down, we could do it yx, but it won't really matter for our processing. So to find a possible beacon location, we take the position of every point on the board. So we'll say is not beacon is if it's not one of the beacon values, and is not sensed is this is not going to be. So we need to find for every sensor, we want to find a sensor that includes this point. So I think we do this. We bring in our filter. The line number in this case is Y. The find in this case, I'm going to name this something else. Well, max distance. Fine. It's fine. It's fine. Distance on line. Then we get the range. We should be watching these tests. Cannot subtract I32 from double reference to I32. That is true. So let's do this. And then this range. Okay. So we are doing all of our distances, which is a sensor and a distance that it can reach. We are filtering out anything that isn't in range of Y. So anything that the Y range can't reach. And then we are finding something that for the Y position that we are on or looking for has an X that is in the sensor range. So this is sensed. So the sooner we find something that senses it, the less work we have to do. So this filter is filtering for the Y range, and then this find is basically finding for the X range. I'm sure there's a better way to write this. I will go back and refactor it, I think. So we know if it's not a beacon, we could just say this is beacon. So if it's a beacon, then it's not a possible beacon location. So we need to find and we return false here, which is a unit return from this if statement. I'm trying to early return to prevent potentially doing more work. Is sensed. So if it's not a beacon and it's not sensed, sensed is an option. So if it is not some, sensed is sensed. That feels a little awkward to write. we do need to start running our second test here. So at least we're failing now. So we've got, if it's not, I think there's an is none. So we'll do is sensed is none. So if it's not sensed, if position is not sensed by sensor, then we get possible beacon location. We're doing a find and not a filter on these, which is fine. We're doing this find, which is something that isn't a beacon and is not sensed. This we might want to be a filter. Filter would require that we process everything, right? If it's possible beacon location, then let's do the find just to get the log. And we get 1114. The question is there anything else? So if y is less than 0, or x is less than 0, or y is greater than limit, or x is greater than limit, return false. And these are all going to be reference issues, which is easily fixed. I don't know that we need this, but it feels like we might need it for the next one, which is much bigger. So this is sum 1114. So let's do let sum beacon equals possible beacon location. Then we do this, else we panic. Oh no, because that's not good. And this is not set up right. I did that for an if let, but we don't have an if let, so I'm gonna do this. And is our mathing. This is going to be beacon.1 because that's the way I'm testing it above, which is really unfortunate. Beacon.1 and 0. So that should be a working test, at least. And I am concerned about running this on the actual input. I'm really hoping this runs in a reasonable amount of time. We may have to optimize it regardless, but at least we have a passing test currently. So I feel like we're doing too much work here for the problem, and we're going to have to reduce the amount of work that we're doing. I am going to have to think about how to do that though, right? Because we generate all of the points and it's lazy, so this gets generated whenever. And then we find a location. That location requires us checking 4 million points per row. So I don't even know how fast this is running. Let's do debug Y, I guess. No, let's do, we need to speed this up somehow. If we're gonna do it like this, the way that I wrote it is extremely parallel. So whenever we find one, we win. Rayon is the thing that I would reach for if I was going to try to do this in parallel. I don't know if we will be able to slap this on before we do the Cartesian product. So I think that we are just going to pull it in and do it after the Cartesian product. So we can just pull in Rayon prelude, something like this. And this is going to be input par iter. I think there's into par iter as well. Yeah, into par iter here. So let's get Rayon in here at least. And then I'll add into par iter here on this iterator. We haven't built, so I'll just run a cargo check. Method not found. We need to bring in the trait, which is going to be like use Rayon prelude star, I think will be enough. That may not be true. We run into method that cannot be called on itertools product, unsatisfied trait bounds. So because it's already an iterator and we can't use into iter on. So let's make the documentation a little smaller. We've got the parallel iterator trait. We've got the into parallel iterator trait, which should work for us. So I can use par bridge to take the iterator that we've generated from itertools with Cartesian product and turn it into a parallel iterator. Immediately we're notified inside of the VS Code editor, and also if we run cargo check or test or whatever, that we can that find is deprecated basically on the parallel iterator trait. So we can use find any, find first, or find last. So we can go look at parallel iterator and say find any, searches for any item. So if we parallelize stuff, we don't necessarily search in order. So we can't guarantee that we will find the first one, but we will find a solution. Now, if we've written our code correctly, there will be only one solution, I believe. Find first would require us to, whenever we find an item, we would then stop everything to the right of it in our vec, let's say, but we would still have to continue everything to the left to do the computation because this is trying to find the first one. Find last is similar, but in the other direction. So find any is the one that we want. So if we do find any and we run this with release, we have to compile it obviously. And now we wait and we hope that it runs faster because it didn't actually finish the first time. Okay, so this has been running long enough that I know that my solution is badly coded enough that the performance algorithmically is not going to work. Rather, I could let this run as long as I wanted to and see if it worked, but I can show you what the part 2 script is doing inside of Activity Monitor. It's running at like 500% CPU capacity. It's using a hell of a lot of CPU time. It's got 11 threads. It kind of impressively is only using 1.8 megabytes of memory. Now that could be because my other programs that I might have open are using quite a bit of it. And I should probably quit DaVinci Resolve. So after removing DaVinci Resolve, I restarted the process just to take a look at what would happen. Our CPU percent climbs to something vaguely similar, 600%, and our memory usage locks in at 1.8 megabytes, which is pretty interesting. Now, that is obviously extremely unscientific, but I did let that program run for like 9 minutes and 30 seconds. So algorithmically, this must be just really, really bad. So I feel like there's a number of other approaches we could take. One is that since there's guaranteed to be only one position, at least in part 2, I think there's guaranteed to be only one position. Yeah, find the only position possible for the distress beacon. So we could, instead of trying to check every point against every sensor, we could check all the sensor coverages of each line. And if we fill out a line, remove that line from possibility. So I'll save this in case you're interested in the code that is here currently. And then I'll start working on a better solution. So calculating the distances for each sensor is probably not a big deal. Let's do something fun like this before we continue. So, I mean, I think this is probably bottlenecked on output to the terminal more than it's bottlenecked on actual processing. But you can see how we're parallelizing right now because we are 504,804 and 504,779. So I feel like we want to work with ranges. So I guess let's start by generating the list of ranges for all the sensors. There's two ways that I can think of doing this or doing it better. One is we can check all of the points immediately outside of a sensor. So instead of checking all of the points that exist, we check all of the points around the radius of a sensor. Because since there's only one point that this thing could be in, it would have to be outside of all sensor ranges. The other one that I can think of that might be a little bit easier since we've already written the code is to basically generate the ranges for all of the sensors, for all of the lines, and then find some way to merge those together, but more specifically count them. And then we can run this algorithm because the algorithm works on that one line. So we only have to do 4 million calculations instead of, 16 trillion. So I think that's what I'll start with. I think I'll start with the sensor ranges, which is this for each of the Y values. So if we do let ranges equals distances dot iter dot map sensor and distance. I think we want to call this max distance, and we definitely want to make sure that we have properly typed that. So we'll return the sensor range here. I guess we could do that with like not sensor dot y, whatever our y is going to be. So we need a loop over this probably. So this is probably going to be a flat map because we could return multiple ranges. We want to do sensor dot y minus max distance dot sensor dot y plus max distance. And this is the range that we need to iterate over to calculate each of the lines. To calculate a single line, we need to do this stuff. What kind of function do we call to actually do that? I guess we can just map over it. Then we just have y. And we're left with what? Each of the y's for the sensor. We map over y. The distance to the line is sensor y minus y. We do this. Max distance is going to be a single dereference. And then we get this range on that line. So what we're returning here is y and the range that it covers. So that gives us the range of every line for a sensor for every sensor. So we end up with a ton of tuples that are y and then the range. It looks like collect can't automatically handle this for us. So what do we want to do about that? We could collect it into a vec of I32s and range inclusives, and then ranges would give us whatever. Let's do a to do here so that it breaks and we see the output. We end up with all of these 0 to 0. So we get a bunch of ranges, a bunch of y values. I don't really want to necessarily evaluate all of these, but we could. What else can we do here? We could do something silly like have a B tree map for the Y position and the low and the high that we've seen for that Y position. So at which point we don't need to collect here. So for Y range in this, we let do this as mutable. We don't collect. We do low high dot entry Y dot end modify with some function LH dot 0 equals range dot min, range dot start bound dot min LH dot 0, LH dot 1 equals range dot end bound dot max dot LH dot 1. That doesn't work because of types of some kind. Max exists for enum bound I32. I'm just going to do into here. Into doesn't work for start, but it works for end. Why doesn't it work for start? It occurs to me that I have not ever looked at what bound is on a range. So the enum bound is included, excluded, or unbounded. It'll always be included for us because we're doing inclusive ranges. But can we, from a range inclusive, just get a tuple? Start returns the index type, so maybe we just do start here. We do need the value and borrow this. We now see the issue here, this and the borrow. So dot start and dot end return the index type, which in this case is an I32 for us. So if we do all of that, then hopefully we hit this pretty quickly. Low high equals empty. That's not great. End modify dot or insert is what we forgot here. What are we going to insert here? The start and the end values, right? Which both probably have to be dereferenced. So we want the values themselves. And then we get the low and the high for all of this stuff, which on our small input runs very quickly. So 2, 2, 1, 3, 0, 4. Here's 10. Then we get negative 224. But don't we have 10 up here too? No, that was negative 10. So then all we need is what? The lengths. So low, high, dot values. No, let's do low high dot iter dot find key bounds dot 0 dot bounds dot 1 dot length. Hopefully that doesn't execute everything. Dot length is less than, I think limit is what we called it. Did we not call it limit? We did call it limit because limit has to be as usize because we're doing a dot length there. So we find that, we debug row, and we get negative 10, 2, 2, which doesn't sound right. We need to see Y11, X14, and we see negative 10 as the row. Is that because I mixed something up here? For Y range and distances, iter, sensor Y, map Y, distance to line. We get the range of X's and the Y. Then we iterate over that using a B tree map. We do the entry and modify. If it exists, we do the range start and we get the minimum between the range start and the left hand, otherwise the range end, and the max. Or we insert the range start and the range end. So let's debug low high and just check to see that we're generating the right stuff. Negative 10 feels like, well, we don't even get the actual like whatever here, right? So it can't be negative 10 by definition. So negative 2 is the closest we get. So row 0 is where we need to start. Negative 8 to 26. That looks right, or at least plausible. Ooh, the one thing we aren't doing is this could be a filter right now for us anyway. We collect this. This becomes a vec of whatever, and we end up with a bunch of possibilities. So find was cutting off early. Do we get the right thing? 24, 25. None of these look right. We need 14, 11. So I'm doing the math wrong. Dang. So if we dump out LH for all of our calculations, then we get stuff like this. It looks like it's doing the right thing here at least. So are we not calculating this correctly? Distance to line, max distance to line. This is for Y range, flat map. This is sensor Y, the range of sensors for the Y index, right? Map over that, get the distance to the line, take the Y index that you're at, along with the range for X, return that, flat map it. I could inspect this. And then we should probably get rid of some of the other debugs here because they'll be pretty noisy. Let's get rid of low, high, but not row. And then let's get rid of left hand. Oh, 0 and 1. Okay, now we're good. Okay, so we get a bunch of stuff, right? This is only logging out. Okay, this is Y and the range, but it's not telling me which sensor it's associated with, unfortunately. 8 and 0. Let's check for Y11s. So 11 is -3 to 3. 11 is 2 to 2. Let's do if x dot 0 equals 11, then print this out. So we get -3 to 3, 3 to 13, 11 to 13, 15 to 17. So we're missing 14. Oh, dang. We need to do this within the range. Oh, damn. So let's do this dot min 0 and dot max limit. So they can only go 0 to limit. So let's ditch this inspect and let's actually, this is not, we don't want dot min here. We want, I think we want dot max here, right? If it goes below 0, and then we want dot min here. And then we end up with a bunch of values that are between 0 and whatever. The problem is that I messed up. We don't need the low and the high because that'll just cover the range. RIP. So I made some small modifications. We get now our low high includes all of the ranges for everything. So we should see in 11, we are missing the number 14 here. I don't want to expand the ranges because that would be annoying for the 4 million solution. I want to find a way to work with the starts and the ends. Here we can cut off doing any processing for anything below 0 or above limit for the Y values. So we get nothing over 20 and we should get nothing below 0 either. That's cool for us. And then we basically have a bunch of ranges and we need to figure out if any of them don't cover a value. I guess we could do the same thing here too with the zeros. So I've changed this to be a range from only 0 to limit. So anything outside of that will get recounted. So now all of our ranges are from 0 to limit. Can't think of an easy way to combine all of these without iterating them all. I guess we could try iterating them all. It is quite a few calculations to do that, and I don't really want to. So if we iterate over low high now, we find we get ranges. Ranges are a double reference to the range inclusive. So we probably want, if we iterate over that, clone it, we flatten, limit as use size. Let's instead of find, let's map and collect for debugging purposes. We need unique. Right. So for that to work, we have to have unique. These are all 21 except for this one. So that would technically work. So we're looking for the one that equals the limit. So now we can find here. This isn't a collect anymore. This is the row. I feel like I'm doing more work. We have to find this. So we unwrap it. We're left with row index and ranges. And then what, we do this on them? Cartesian product isn't something we need anymore because the Y is always going to be the same. So really what we need is 0 ... equals limit. And then this doesn't need to be par bridge anymore. This can be into par iter, I believe. This will be X. And I'm just going to let Y equals row index right above this for now. And theoretically that works. What are we missing? We're missing something. Possible beacon location is now an I32, so it'll be the X value. So it'll be X plus Y, 2 string. And this has to be, what is this? Why am I, it's an I32. We'll call this beacon X. And that passes, and is this even going to help is the question. Like if we run release part 2, I feel like I haven't really fixed anything because I still iterated over every range up here. Part 2 now taking significantly more memory. So it's taking almost a gig. It doesn't seem to be growing. The CPU is down to 100%. So I probably need to par it or something. I think because this is mutable, this is holding us back a bit. I'm 99% sure that the counting is our problem here in terms of runtime because we are doing all of these ranges. I feel like I can't think of a way to merge them, but that feels like the key to unlocking this runtime so that we don't generate 16 trillion numbers, which is what I'm doing right now. Yeah, look at how slow that is. That's how fast we're doing the 4 million like range evaluations. That's so slow. I feel like the first thing I want to do is see what just throwing par iter and find any does to this. So we get, 11 times the speed is what I'm going to call that offhand. Definitely not enough of a speed up. So to keep it visible, let's do this. So if we don't iterate and we just check every number, it looks like we get a significantly faster output. So we don't need to iterate over the range. We can just do range.contains option unwrap on unknown value. So we just hit 4 million. So if we go from 0 to limit and we try to find the I that doesn't exist in the range, in any of the ranges, any range contains I sounds right. If we iterate over the range, any range contains I, then nothing. So our issue for the compiler for this is expected bool found unit. That's on this. Missing closing delimiter, any, and it goes up like this. Expected bool found option from. So if we do 0 limit, find I where not any of them contains I, and we do find map, then this is the X value that comes back. So if this is sum, then we want to map over it. We get an I32 out of that. So we do X key is Y. So we get XY there instead. And do we even need this second part then? Because we've already found the X that those ranges don't contain. So we get rid of all this code, get rid of this. This goes X and Y. We run that. We see how fast it goes, hopefully. Much slower than before. That is very slow, actually. What did I do to slow that down so much? So I think I'm just going to throw that approach away and do, if I have a bunch of ranges, I know they're going to split into two. So how do I merge a range without evaluating it? So if we do ranges.iter.map or ranges.iter.windows, right? Tuple windows? No, ranges.iter.fold. We'll start with 0.0, I guess. So I know that there's going to be a second range for one of these. So I want to accumulate into the first range. So if act.end, act.0.end is less than range.start, that's the wrong thing. If the end of the first range is greater than the start of the second, because these are in order, then we get act.0 equals act.start no method start found for tuple. That's because it's acc.0.start. Expected NaV32 found a reference, and that is on start. And then none is no type. So let's do let result equals this, and then we can set the result equal to a range inclusive I32 and a option range inclusive I32. And actually, I don't think we need the range for the second one. I think we're almost guaranteed to have this as an option I32, or at least we can calculate it like that. So this can be none, yada yada. If the accumulator range, accumulator needs to be mutable, of course. And then that technically works. We still need to figure out what happens if this is not true. So if the end of the first accumulator is greater than the start of the second, I think it's greater than or equal to, right? Greater than or equal to the start of the second, then we do that. Else acc.1 equals acc.0.end plus 1. Is that right? What's our type issue here? This needs to be sum. If acc.1 is sum, return acc. Otherwise, we do the actual calculation. And then what do we get? Debug result. For this, it's 0 to 20 and none. For most things, it'll be that. So if we return result.1, we map over, then this is now the wrong thing. This is now not a vec. Well, this is a vec of option I32s, right? So if we find map for result.1, then we get an I32. So we don't need to collect. And I did that wrong. Expected I32 found enum option. Okay. This is the find map. The result is returning the option, which is going to be what find map needs. Expected I32 found option. Let's expand this and read it. Low high int iter rs I32. Oh, this is going to be an option I32. That's fine. I mistyped my rs thing here. So panicked assertion failed, sum 14. So this is going to be X. We'll unwrap this to get the I32 because we always need to have one. Otherwise we've failed. And then is that enough? We need Y. Did I toss Y into the wild beyond? Ranges.iter.fold. Find map key. We need key here. So let's do, we need result1 dot map X key XY basically. And then this turns into, this is I32, I32. This is not X, this is XY. And then our test passes, at least. And then we try to run it on part 2 and hope that it runs. Okay, that is significantly faster. I think we're at 2 million there, and we're probably losing to the console. That's the wrong number. So let's give that a whirl. That's not the right answer. Answer is too low. That's not great. Hey, editor Chris here. This is actually the right answer. It's just a problem that I used I32s for all of the numbers, so the calculation actually overflows. If I use I64s at this moment in solving the problem, then this is the right answer.